So far, we have derived an equation connecting the nodal displacements and the nodal forces for a single element. Now we have to write equations for all the elements and then combine these equations to form a global equation. This process of combining the element equations into a global equation is known as assembly. For simplicity, let us assume that we are dividing our domain into only two elements. For element 1, the local numbering are 1 and 2, and for the element 2, the local numbering is 1 and 2, and the global numbering is 1, 2, and 3. The displacement at the node 1 is u1, at the node 2 is u2, and at the node 3 is u3. And the force at node 1 is F1, at node 2 is F2, and at node 3 is F3. Note that we are using global numbering to represent both the nodal displacement and the nodal forces. So we have two elements, the element 1 and the element 2. For both these elements, the local numbering is the left node is 1 and the right node is 2. And the global numbering for element 1 is 1 and 2. And for the element 2, it is 2 and 3. This is local numbering, and this is global numbering. This table is known as the element connectivity table. Now let us write the equations for the element 1 and element 2 using global numbering. When writing the equation, we now consider all the nodes. So the displacements would be u1, u2, and u3. And the force vector would be F1, F2, and F3. Now for the element 1, we know that the nodes are only 1 and 2, and the node 3 is not included in the element 1. And there are only two equations, and they only include u1 and u2 and f1 and f2. Therefore, the last row would be 0, 0, and 0, since there is no third equation. We also know that the coefficients of u1 and u2 for the first two equations are like 1 and -1 and -1 and 1. And since u3 is not included in the equation, the third term which gets multiplied with u3 would be 0 and 0. So this term gets multiplied with u3 and this also gets multiplied with u3. If you multiply this matrix, you will get two equations as Ea by L into u1 minus u2 is equal to f1, and Ea by L into minus u1 plus u2 is equal to f2. This matrix is known as the expanded matrix. And the reason why we write this equation in this form is that we can easily combine the element equations. Now for the second element, we know that the node 1 is not there, which means that u1 and f1 are not the part of equations. Therefore, the first row would be 0, 0, and 0. The element 2 only has the node 2 and the node 3. And we know that for the node 2, the coefficient of u2 should be 1, and the coefficient of u3 should be -1 here, and here it is -1 and 1 again. And since u1 is absent in all these equations, the terms which gets multiplied with u1, the first elements in the row, should be 0 and 0. So we now have the equation for the second element, and this is again the expanded stiffness matrix of the second element. Now we can assemble these two equations to get the global equation. For that, we can add the expanded stiffness matrix of the first element with the expanded stiffness matrix of the second element. So the global stiffness matrix K is equal to Ea by L, that is common for both, and we can add these two matrices. The first one is 1 minus 1 0 minus 1 1 0 and 0 0 0 plus the second matrix, which is 0 0 0 0 1 minus 1 and 0 minus 1 1. This equal to EA by L into, the easiest way to add these is write the values 1 minus 1 minus 1 and 1 here, and for the second matrix it is again here 1, so this 1 plus 1, and you have a minus 1 here and minus 1 here and 1 here, and the remaining terms are 0 and 0. Note that the only term you need to add is the middle term, which is for this value in the first matrix and this value in the second matrix. So we have the global stiffness matrix K is equal to EA by L into 1 minus 1 minus 1 here 1 and then plus 1 here minus 1 minus 1 1 and 0 and 0. And our global finite element equation is of the form K into the displacement U is equal to the force F. So let me expand the global equation, which is EA by L into this matrix into the global displacement vector is equal to the global load vector. Now, if you solve these equations, you will find the displacements when the forces are given, and we know the material properties. E is the Young's modulus, A is the cross-sectional area, and L the length of the element. To solve, we also need to substitute the boundary conditions and the load values in the global displacement vector and the global load vector respectively. We will see how we can solve this equation and obtain the displacements u1, u2 and u3 by substituting the boundary conditions and the forces using an example problem in the next video.